Okay, Assalamualaikum warahmatullahi wabarakatuh. We continue our chapter 4 in case 3. Okay, this case 3 in example 4.8 to find the Q. Okay, a 100 mm diameter and 120 meter length of cast iron pipe was used to flow an oil and cause 5 meter of energy head loss. So if viscosity is this value, determine the flow rate of oil in the pipe. Okay, the solution. So look at this is the value is given. So D diameter is 100 mm, velocity, viscosity, and the length HF, and the E is for the types of pipe. So you can find it from the Moody chart. Okay, assume fully turbulence, try and error solution. So in this case 3, you must use the try and error solution. Okay, for first you must find the roughness, E, relative roughness, so E over D. So you find the 0.0025. So using the HF, okay, using the head loss equation, friction loss equation, so you use this equation to convert to this, okay, velocity in terms of this pipe. Okay, so from this, okay, from this HF to this equation in terms of velocity, and Reynolds number is using velocity times by D and the viscosity. So using the trial 1, okay, so we use the F trial is 0.0025. Okay, so we can use the trial for F, must use from 0.020 above to the from the Moody chart. Okay, from 0.020 and above, so you can try using the F. So use this formula, okay, velocity. So you just put the F try F L 2G D, and you find the HV HF, you find the HF. So we get the velocity 1.81 meter per second, and the Reynolds number 1.81 times by 10 power of 4. So from this equation, from this value, okay, you must find the friction factor again from the Moody chart. Okay, so from the Moody, you must continue the F trial. Using the F try F2, you must using the F trial you get from the trial 1. So you use the 0.031. So put this F to the equation V and the Reynolds number, so you get the value of the velocity in this part and the Reynolds number. Okay, this is just correct this for the Reynolds number R, Reynolds number. So we get this. So after you get this one, so you just must look at the Moody chart to get the F new. Okay, so we get the F new 0.031 is the same as F trial at the F1. So 0.031 is equal to F new, so it's okay. So you just stop at this part. We use the F new of 0.031. So we get the velocity is 1.62 meter per second, and the Q is equal to velocity times by A. So we get the value of the Q. Okay, so in case 4, to find D. Example 4.9. So in this case, the HF, L and Q are given. Then you must find the diameter of the pipe. Okay, so this case, so determine the suitable diameter of galvanized iron pipe in flowing 85 liter per second of water at length 180 meter. Okay, 180 meter with 9 meter of fluid friction. Okay, so given viscosity with this value, so solution here for the case 4. So all these, okay, all these parameter is the value is given in the question. So you must use the Reynolds number. Okay, so Reynolds number is equal to V times by D over viscosity. Okay, or you use the V velocity because we don't know the value of the velocity, so they give you the Q, so you must use the Q over A times by D over by viscosity. So from this you convert to this one, so just put the value here. So the Reynolds number in this value in terms of D, diameter. Okay, so D. So we use the HF, FL V squared over 2GD. So you just convert here. The velocity you must change to the Q in terms of Q here. So we get here from this one, so you get this one and you get the diameter and convert to this equation to the in diameter. So we get the diameter power of 5 is equal to FLQ Q2 QQ squared over 12.1 HF. Okay, so from this equation, so you can find the using the F here. Okay, put all the parameter value to this D, so we get the diameter power of 5, 0.012 times by F. Okay, so solution here. So try and error, also use the try and error solution. So you use the formula D. Okay, start by assuming a mid-range value of F. So from the previous slide, I said that you want to try the F trial, so you must use from 0.020 and above. So in this case 4, we can try the F trial 1 using the 0.030. Okay, after you use this trial F, you just insert all the value to the D and the Reynolds number, and you get the diameter of 0.2045 meter and get the Reynolds number to this one. And you must look at the Moody chart and find the E over D. Okay, find the E over D. You get the 0.00073 and you get the F new from the Moody chart. Okay, but the F new is not the same as the F trial here. Okay, so you use the F trial second at the second stage. You use the second trial using the F new that you get. So F trial 0.019 and insert the value to the D. So you get the D 0.189. Okay, 0.1869 meter and you get the Reynolds number, this one. And E over D, you get 0.008. And you get the F new from the Moody chart 0.0195. Okay, so this F new is near the F trial that you use 0.019. So we just stop at here. Okay, we just stop until to trial 2. So we use the F new as 0.0195. And we get the diameter is 186.9 mm. Okay, In design, standard size usually will be chosen from tables shown in the next slide. Okay, so we get the size normal pipe. This is inch. Okay, standard of iron pipe. Okay, so we can use. Okay, this is just in the standard, so we get the diameter. The galvanized iron is this one, so this is in the range. Okay, so it's okay. So the diameter is the right value that you get. Okay, so we continue the minor losses in pipe. Okay, the previous slide that I explained is more on head losses in friction pipe. Okay, head losses in along the pipe. Okay, but in this pipe, I will cover the minor losses in pipe. So the minor losses using the symbol of HM. Okay, so minor losses mean losses due to local disturbance of the flow in conduit, such as change in cross section, projecting gaskets, elbows, valve, and similar items. Now, the causes of minor losses are usually confined to a very short length of flow path. The effects may not disappear for considerable or distance downstream. Okay, minor losses such as usually used in piping system include fittings, valve, bends, elbows, teeth, inlets, exits, enlargement, and contraction. Okay, these components interrupt the smooth flow of fluid and cause additional losses because of flow separation and missing. So we introduce a relation for the minor losses associated with these components using the HL. Okay, HL is equal to KL times by V squared over 2G. Okay, HL is the minor losses. Okay, minor losses using the fitting, valve, bend, elbows, teeth, inlet, and so on. Okay, the minor losses. Okay, the minor losses for the fitting, valve, bend, elbows, teeth, inlet, exits, enlargement, and the contraction. Okay, so we use this equation for minor losses. So KL is the loss coefficient. So the loss coefficient is different for each component. So it's assumed to okay. So we look at the minor losses in pipe. So minor losses can express by HM. Okay, minor losses HM is equal to K is the coefficient, V squared over 2G. Okay, also can represent them as being equivalent to a certain length of straight pipe expressed in terms of number of pipe diameters. Okay, K or an F loss coefficient here. So minor losses also known as H or where it happened. HE is loss of head of entrance. Okay, so example here for if the HE is the loss of head at entrance. Okay, so this look at the loss of head at entrance. Okay, this is happen when fluid from reservoir enters the pipe in figure at point B here. Okay, at point B here. Okay, velocity is maximum and minimum pressure. So this is called the vena contracta. So we use the HE, okay, head of at entrance. So using the KE, okay, V squared over 2G. Okay, so this is the minor losses in entrance. Okay, so we look at loss due to the entrance of flow into the pipe. HE is KE times by V squared over 2G. Okay, KE is the coefficient loss. Okay, loss coefficient KE. So in this case, KE is equal to 0.5 because this is using the square edge flush. Okay, this is a square. But for the bell mounted, this is called the bell mounted, so we use the KE is 0.04. Okay, for the square edge flush, so 0.5. Okay, this re-entrance, so KE over 0.8. So don't worry, this coefficient will given in the test or in your finals, because in the text is given. So just no need to worry. So you just how to know what is the square edge, what is the bell mounted here. So if the KE 0.5, automatically see this coefficient is for the square edge for flush here. Okay, loss at head at entrance. Okay, so using the submerged discharge of this one, okay, at the submerged discharge, because the flow from the pipe submerged discharge to the reservoir here. So that's why the KD coefficient of the submerged discharge here is 1. Okay, so loss of head when pipe discharge fluid into field reservoir or the tank here. Okay, that's we use the HD for the discharge is equal to KD V squared over 2G. Okay, so loss of head due to contraction. Okay, so you use the contraction, so we use these equations HC. Okay, HC is for the contractions is equal to KC V to square over 2G. Okay, the contraction is between the big diameter here. Okay, the bigger diameter of the pipe to the enter to the smaller. So this is called the contraction between the big pipe to the smaller pipe. So this is called the contraction. Okay, loss coefficient for sudden contraction is between D2 over D1. Okay, D2 at the bigger diameter to the smaller diameter. So we get the KC here. Okay, so the diameter 1, the diameter 2, they give you the diameter 2 over by the diameter 1. So we get the KC from this table. Okay. So loss of head when flow contract for smooth curve transition, KC can be as small as 0.5. Okay, this 5. For conical transducer with angle here, minimum KC is about 0.1. Okay, so no need to worry all this. Okay, so this is loss of head due to expansion. Okay, loss of head due to expansion, we use this equation. Okay, V1 minus by V squared, V1 minus by V2 power of 2 divided by 2G. So this is called the sudden expansion. Okay, suspension when the smaller pipes enter to the bigger pipe. So this is called the sudden expansion. Okay, small to bigger pipe. Okay, this is called expansion. But for the contraction from the bigger pipe to the smaller pipe. Okay, so this is the expansion using this figure. Okay, so actually for the kx is also given, so v1 and over v2 is also given, so no need to worry about this. Just know that what is the coefficient of the fitting. Okay, fitting, bends, contraction, sudden, okay, sudden, submerge or something else. So using the fitting. Okay, so this is the fitting such as valve, bend and the elbow. So we use the K for the fitting using this. Okay, this is the types of fitting and this is the coefficient. Okay, when the fitting using the angle valve wide open, so the K is 5. So this is this equation for the pipe fitting. Okay, so all the value will given. So need just for theory that you can understand how to use it. So loss of head due to bend and elbows, so using this, okay, HB, or using this loss coefficient due to this one. Okay, so loss in pipe fitting. Okay, so this is happen when fluid flow through pipe fitting. So this table always given in your final, okay, and your test. So just using the type of pipe fitting, so you use the K, and L over D is length over D diameter. So velocity in the pipe of the nominal size of the fitting here. Okay, so use the HB for the bend or something else to the pipe fitting is equal to KB V squared over 2G. So look at example 4.10. Okay, water flows through a 150 mm diameter pipe at 100 liter per second. Okay, if the pipe suddenly enlarged, okay, the pipe suddenly enlarged, okay, to 200 mm diameter, find the head loss. Okay, if the same enlargement is via a diffuser with a total cone angle of 20 degrees, what is the head loss? Okay, so this is using the cone angle. So so look at the solution here. So the value of A1, A2, Q, and also the angle here. So you must find the velocity 1. So we get the 5.66 meter per second. And the velocity 2. So we get the 3.18 meter per second. Okay. Using the A1 and A2 here. So you can find the V1 and the V2. Okay, using the same Q here. Okay, for the sudden enlargement, so you use this equation. Okay, and we get the H for sudden enlargement is this value. Okay, for the cone angle here, okay, you look at the previous slide to find the angle with 20 degrees. So you can find the K is, okay, when the cone angle is 20 degrees. So we get the K from the table 0.838. So you just insert the value K to this equation. So we get the value of cone angle here. Okay. Look at the example 4.11. So we have the tank here, elevation level 4.1 here, okay, and 0.2 here is 24 meter and 30 meter respectively. Okay, so determine the required air pressure in the tank. So the P1 here is needed to flow 0.013 meter cube per second of water to 0.2 here. So consider all head loss. Okay, so this is consider all head loss. So it's given length for the pipe here 152 meter, diameter of pipe 150 mm, and the F this one, and the KE for the KE at this stage entrance here. Okay, so we solution here. So this is all the value given. So you must find the first, the V2 velocity 2 at 0.2. So we get the 0.74 meter per second. Okay, so using the Bernoulli equation, energy equation, so you must put at the 0.1 here. Okay, and 0.2 here, but include all the losses. Okay, in text all the losses is include. So losses friction along the pipe is HF plus the minor losses at entrance. So this is called all the losses include. Okay, Bernoulli equations must plus the HF plus the HM here. Okay, so we know that the velocity at the point 1 is 0 and the point pressure at 2 is 0 because it is atmosphere. Okay, the pressure at atmosphere for the P2. So this is 0 and this also 0. So we just get the P1 here. Okay, and Z1 and Z2 here. Okay, so we know that HF is using this equation FLV squared over 2GD. Just input all the value to this side. So we get the HF in terms of value velocity 2. So you just put the value of velocity to 0.74 meter per second. So we get the HF and we get the okay. So these equations we get the pressure at 1 just velocity 2 plus Z2 minus by Z1, you get this one and you get this one. So until we get the pressure at point 1 here, you get 75.5 kilopascal. Okay, for the pressure at 1. Okay, so look at the other example 4.12. So water, okay, at this degree is being pumped from a stream. Okay, from the stream here, pumped to the reservoir whose surface is 64 meter above the pump. Okay, 60 meter from the pump. The pipe from the pump to the reservoir is 8 inch. Okay, 8 inch in steel pipe along if 0.113 meter cube per second is being pumped, compute the pressure at the outlet. Okay, pressure at the outlet here. Okay, consider the friction loss, all the friction loss in the discharge line, but neglect other losses. Okay, so this is but neglect other losses. So there's no losses in fitting, just only have the losses in friction loss. So if the pressure at the pump inlet is negative 16.27 kilopascal, so compute the power delivered by the pump to the water. So look at the solution here. Okay, so the solutions for this question, so you must know using the Bernoulli equation. Okay, using the Bernoulli equation here. Okay, using the Bernoulli equation here. Okay, energy equation between A to B here. So PA plus ZA and so on HF. Okay, because they have the HF from part this one, you just negative here. So we get the equation here. So Reynolds number, we know that we get the Reynolds number here. And from Moody charge, we get the F. Okay, so just put all the value and after this you find the P inlet. Here is negative 61, P outlets will get the P. So power delivered by pump to water, you use this equation. So we get the pump power is 112.8 kilowatt. Thank you. Assalamualaikum warahmatullahi wabarakatuh.